Okay, hello everyone. Welcome to another design review, part of our season of version 14.0 design reviews. This is part 2 of calculus and algebra. And let's see, last time we did talk a bit about the graphics of the finite field indicator. Did we make any more progress on that?
There are four well, Itai is here, so we could have that discussion more in detail. But there are four functions that was triggered by the discussion at the top there.
Okay.
Last design review, so they've been implemented and documented.
Finite field element index as opposed to finite field index. Okay.
Right, which is consistent with, right, the thing it takes is a finite field element, not a finite field.
I understand that it's a bit long, but my God, we're now at 5-word function names. How many 5-word function names do we have in the system? That's the kind of trivia one should be able to ask an LLM, but one probably can't. Okay. God, I hate doing this. I hate having this FF equals and then this. I really hate it. Don't know why we do that in examples. It just seems silly. It's like, why have the extra cognitive load of having to understand that?
Well, in this example, it has no purpose. Oh. And also, the other thing is when they're nice typesetting, like graphs and other things, it's nice to have them expanded.
Yes, when I agree. Okay. All right, so two finite field coefficients. What is this doing?
That's
a little different from what we talked about before.
It converts the rational function or a polynomial to finite field polynomial rational function.
Why is the name right?
All the coefficients are turned into finite field elements, or the numeric coefficients.
Okay, you know what? Why isn't this two finite field element coefficients? I don't understand why we have to have the word elements in here. It's an index in a finite field. You know, we've got other functions that don't say in pedantic detail every detail of what they're saying. I don't think there's any different meaning that finite field index could have.
Also, it's listable, so I guess that, these are listable. So element seems to think there's only one element involved, but it could be several of them. So maybe that short name is much better. I guess you're right. Finite field index looks better.
Although we have finite field element norm and finite field element trace.
Right. So for specific element, this one actually takes a list, right?
Or it can take one element. It's just not very useful there.
Yeah, so I'm just saying that in that sense, having the element out would also avoid some confusion that it only works for one element.
Yeah, let's hear about the norm thing. What is the norm thing?
So
you're saying, go ahead.
So it's a quantity that's associated with every finite field element, and it has norm and it has a trace.
Okay, but that is of an element. People would say it's of an element. I mean, I understand they would also say it's an index of an element, but I mean, let me see the guide page. Is it in here?
Yeah, should be.
Hope. By the way, I just want to comment for whoever's PMing. It's still too slow to bring up the root guide page. And by the way, you're missing a tagline here. Who is PMing here?
I am. Tracy is.
Okay. So, and you don't have an intro there yet. I don't have any problem with this. I mean, I think if we say finite field index, Roger, do you have any comment here? I think it's okay to say finite field.
I think it's okay too. I can't see that index could point to anything else.
Okay. All right. Now, why is this to finite field coefficients? It's making the coefficients be in a finite field.
Yeah, so it's you have a polynomial over integers. It gives you a polynomial over finite field. So the coefficients go to finite field.
I know, but really what it's doing is it's converting the polynomial to a finite field.
To a polynomial in a finite field, yeah.
Yeah. It's not really the coefficients. I mean, yes, it happens to be the coefficients, but in normal language, you would say it's a polynomial over a finite field.
Right, but it's not something in the finite field, so it's not taking something and putting it in the finite field.
But it's polynomial over the finite field.
Yeah.
How do we deal with extensions? Polynomial, is there anything where we put something in an extension field? How do we, if we take a polynomial and we factor it and we say extend it over root 2, for example, how does that look? Do you understand what I'm asking?
There is no such thing there because, well, if it's a polynomial, you do extension, it goes to square root of 2, yeah, something like that, yeah. But the polynomial itself, you cannot, transform the coefficients into the extension without factoring it. Like it will still be the same coefficients.
I get it. So if I were to do this, and I were to say modulus arrow 2 or something,
that will complain.
Okay. But this is equivalent to two finite. I hate two finite field coefficients. I hate it. Why isn't it working? Why didn't that work? Why doesn't
One
that
day
work?
too old.
First, yeah, it's maybe
You got
old.
committed last night before last night's build.
Okay. That is a true hall of shame that Arnaud just found.
What?
Functions with five words in their names.
Oh.
Yeah, well, many of these are deservedly 5 words.
Yes.
Okay. I don't like this name. What other possibilities do we have?
So I would like to say polynomial, but it's kind of rational function, so it's a little bit. On the other hand, we generalize expand and other things to rational. Two finite field polynomial.
I mean, there's always two finite field.
I think that two finite field looks perfect because it also works for constants, and you don't need to worry about.
Yeah, that's true.
Does it work? So don't we have another way to do it for constants?
No, I don't
just
think
say
so.
finite field, right? It's just the finite field element. Doesn't finite field element do that?
Nope.
That's a constructor, basically, right?
Well, so if I say I'm going to get 5 mod 2. Oh, no, that's stupid. 5 mod 7 or something. How do I do that?
So 5 mod 7, yeah, then you can do finite field elements and then field index. I think that's the syntax is.
What?
Well, you have to give the field to finite field elements. So you have to first construct the field.
So, for example, as a simple syntax, we could just do this.
And that should make 7 a prime field. Need a prime field.
Yeah, and I mean,
Yeah,
honestly, if I might say so, there is a unique field of a given degree, right, of a given order. So if I had 49 there, it's the field, GF7 squared.
Then it's not unique anymore. You can have different polynomials defining it.
Is that right? Well,
yeah. They are isomorphic, but they aren't the same.
But don't we have a canonical one?
We have well, it's not really canonical. It's the one that we are getting. We have the default one. Yes.
Okay, then we should do that. If I say this, we should use the default field. How do I otherwise construct? Sorry, I'm forgetting this. How do I get 1 angle bracket 1 f, whatever it is? How do I get?
You construct the field and say f of 1.
Okay, so hold on. So I say finite field of 7, for example.
Of 1.
And of 1.
Like that.
Mm-hmm.
Well, there's a really good reason to have a function called toFiniteField then. Right, because that would just look like 1, 7.
And that could potentially work for slightly more general things beyond rational functions as well.
Yes.
Okay, and so if you are saying that it should also work for 49, then I guess finite field should also work for 49.
I think so. I think so. Give the default finite field.
Mm-hmm.
Because I think people will actually write it as 7 squared and it'll evaluate to 49, but then we need to untangle it. Okay, let's talk for a minute about this puppy. I mean, do we have anybody from design here? Can we see if we can get, could somebody see if Jeremy is available just for a couple of minutes?
Sure.
I just think there's too many boxes here. And that the 5 squared is not, it's not integrated enough with the pox, if you get what I'm saying.
Right.
There is a background there.
But I can't see it.
Okay.
I really, really can't see it. I mean, maybe if I put this on, I absolutely can't see it. If you tell me that's not white, I'm amazed.
It's not white.
Okay, I'm amazed. All right.
It's the same color. So if you go to the expanded state, it's the same color that you have above and below the finite field there. It's just it's small enough that you
Yeah, I see. It doesn't work. Okay, let's see whether we can get somebody from design and let's work on this.
I mean,
I'm here.
Okay, all right. So you see this creature?
Yeah.
Okay, what we're trying to do is, I think, okay, I got several questions. Is it obvious that the angle brackets should be fully black? Because to me, really what we want to do is, this is a 1, but it's a special kind of 1 that is in this finite field, which has an opener that tells you more detail about it. So I'd like to speculate what would happen if these brackets were a little gray. And then this thing, in the closed state, we want to see some kind of effiness. I mean, why is it called F? Is there any notation in math? I mean, usually it's called GF, whatever it is, right?
Field.
Yeah, but that's just for a field. But why? When you write out, GF 5 to the 2, you write that GF of 5 to the 2, don't you? And what other notation?
Well, but you wouldn't use a double struck GF. You would.
No, I know. But what other notations are there for a finite field? There's Z mod, whatever it is, but that's
K for Körper.
For what?
Körper, which means field.
German.
Yeah.
What is the word? I thought field was what is the word?
Körper. K-O with 2 dots above it. R-P-E-R.
Like corpse.
Like K-O-E, which you wouldn't like.
There's another word for field in German. It's completely different. Isn't there? Not a field of this kind, but a field like
right. Those are, I don't know what those are. I have to think a sec.
Okay.
That's a different thing.
Oh, Feld. That's the word I was thinking of.
Right, but that's field like, quantum field theory.
That's the field I was thinking about. Okay. So this field is some special name for field. Okay, fine. Okay, all right. We need ideas here. So, I mean, the F, this F could be a lot smaller. I mean, it really is.
Well, it could be a little smaller. I wouldn't say a lot smaller, right? Because you still need to be able to see that there's a down chevron there.
Yeah.
Right, and but both these colors and the F itself were given to me by Jeremy. It's not like
I understand. I understand. Okay, so
do we? I mean, we had a little bit of that discussion last time, but a lot of the real estate is taken up by showing 5, to the second.
Yeah, can I raise another question? In the new design for root objects, what's that going to look like? Because what I'm wondering here is maybe we could get the down chevron not to really be there, but to just be a hover.
Right. So, I mean, I guess I hadn't made a decision. I'm not far enough along to tell you whether there will be a plus sign or a chevron or just a hover. But right, the basic idea was that we would add after the ... like parentheses deg : 3 and or transcendental if it's a transcendental root, and
equals 0.
And yes,
the thing that drives me crazy here, I want a raft that allows me to easily get out the root.
And then, and if you let me finish my sentence, Stephen,
okay,
then you would hear me say that, right, and then there would be an opener state that would allow you, which would display the full polynomial. I mean, we'd need to have some sort of line wrapping or something, right? Because these polynomials can be arbitrarily large.
Yeah, absolutely.
But
so what about the possibility? Okay, so what we've done here is this 1 is similarly as encapsulated as that creature. That is, to get it out, you need to apply a function, right? So I'm wondering whether we should go for a similar kind of look, where we have, instead of the, that root sign thing,
a field?
Yeah, something which is a field sign, and then this just says 1, and then it has a very tiny, or even, and then there's mostly a 1 there, and maybe even using the same motif as these. You see what I'm saying? Because they
just
are really the same.
Basically different icon.
Yeah, different icon, and but then we also need the information. So you're saying in here we might want degree 5.
Right. So one of your complaints was when we last discussed this, which was March, maybe, you complained that you not only could you not copy out the polynomial, you didn't even know what kind of polynomial it was. Yeah. And so you wanted some indication, even in the closed state.
Yep.
So that's when we came up with, deg : 6 or transcendental, etc.
Do we have a design for that? Graphic design for that?
We do not.
Okay, because to me, deg5 and gf5 to the 2 are sort of the same type of information somehow, roughly, maybe approximately.
Okay.
I kind of feel like this design is a lot more civilized than these things that have this, many bits in them, so to speak.
Mm-hmm.
Even than the angle brackets. I mean, to me, putting something in here that just says, forget the angle brackets. It's just an icon and a 1, and then something indicating it's 5 to the 2. What do other people think about that?
How important is it to know what prime power field they live in all the time?
I think it depends on how many of them there are.
Absolutely.
I mean, if there's just
but I'm
two
thinking that in most applications you're going to have one running around only.
No, I agree with that. But I'm saying if you see a polynomial with 2 coefficients in it and they're in GF2, that's worth seeing. Like it's a shift register, polynomial thingy. But if you've got hundreds of them in a polynomial, it's just a nuisance, just noise.
So it's almost like a date format or something. They're sort of differently compact date formats.
Yeah.
Okay, so there kind of can be a short form and a long form. So something that says basically whatever that little icon is that says it's like a finite field icon.
Yep.
And the index, could be the short form. There could be a long form, which also gives the prime power.
Right.
It's almost like it's kind of different length. It's sort of different detailedness. Because I think
I'd like to ask the following question. If we put a small number here, right by that icon, we put a little notation here. I do not like the idea of having a deg, I think it's like, we tend to spell things out, but if we spell it out, it's too long.
Yeah.
And I'm just kind of wondering if, Jeremy, are you in a photoshopping mood here?
Sure.
Just see if we can put like a little tiny 5 underneath there. Not inside the square root, but just as like a footnote 5 type thing.
So outside of the circle or underneath?
No, I would say crossing the circle.
Okay.
And what I'm imagining is something for this with an F there and a little 5 to the 2 tucked inside it. So you're not really wasting space on the 5 to the 2. It's just part of the field icon. Now, it's going to be slightly annoying that we're doubling the length, because if we just have a 1 there for the field element, and most of the time, the field indices will be quite small. But I think that's...
Well, it depends on your applications. Like if you're doing cryptography, the field elements will be quite large.
How large?
Like hundreds of digits. I mean, we won't show all of them, but...
I see. Okay. Look, this is what I'm suggesting. This is what I think. I think that we should use this motif, and maybe Jeremy can mock some of these things. Okay, and then in terms of,
I wonder, sorry, but just thinking, do we in the root case, do we really want that to be a subscript and not a superscript? Because
it might be better as a superscript. It might be nicer as a superscript. I agree. It's a cool idea to have it as a superscript.
What will happen is with other types of roots, like a root of transcendental function, or
will you put infinity
some
there?
Other notation there. I mean,
you could put infinity there.
If it's a nested root object, you compute the product of all polynomials.
I mean, what is it that you want to know? I mean, if you want to know super detailed, you look up the inners.
Right. So, but what do we put in the icon? Like nothing, or?
No. Hold on. What are the cases? There's a plain Jane polynomial. We put its degree.
Yes.
What's the nested
there is a
polynomial?
collection of polynomials.
What's that case? How do I get that case?
So it's a root of triangular polynomial system, and there is a whole triangular polynomial system in there.
Okay, so there are multiple polynomials. So there's degrees 5, 7, or other multivariate polynomials where there are multiple.
Yes.
There are multivariate polynomials, yes.
Okay, so tell me what information you would get. If I asked for the degree of a multivariate polynomial, what would I get?
Well, each of them has a main variable, so it makes sense to have a list of degrees, but it may be a list of several elements.
Okay, but so in that case, we would have 7, 1, 2 up at the top there. And if it gets too long, we just do 7, dot, dot, dot. Does that make sense?
Okay, and for transcendental, it's just infinity.
What's a symbol meaning transcendentalism, so to speak?
Well, it's not algebraic.
Well, I'm aware that that's what it means, but I'm just asking, just like we have things like Z for the field of but for integers.
I mean we don't have a symbol, right? It's R/A, right? It's the reals minus the algebraics.
Yeah, right. But so there isn't a standard symbol for the transcendentals. Well, then an infinity is kind of cool. It's stylish, I would say. I don't know how else we can explain it.
I think that there should be a more abbreviated version of these where you don't have all that clutter.
Well,
that's like a full form date or something. Like
no. But a little tiny infinity there is not. That's not adding space to this. This is what you're getting. It's this, but just with a little notation there. I think we can make it look reasonable.
Okay.
I think that and I think we should do the same thing for the finite fields.
Okay, I can play with that.
Well, I think Jeremy hopefully will. Jeremy, let us know if you have something to show.
Okay, I'm pretty close.
Okay, we'll go on and just interrupt when we're ready. Okay, what's next to look at here?
I think you went through. Maybe we didn't talk. Yes, we did talk about solving as well. So
we talked about all of those things. We didn't get to much on structured array.
Exactly.
Okay,
yes,
so let's go there.
Yeah.
Okay. Do we want to do that, or do we want to try and look at some of these other ones?
I think the calculus ones are probably a little bit more, important.
Let's look at those today, and let's know that we haven't looked at these structured matrices, because I think the structured
one idea we have eventually. So I think we have maybe one plus release away from wrapping the whole thing, and one idea we have to promote it is to write a book, like a handbook, one for each structure, basically.
Good. Well, I mean, I assume there's a guide page of all the structures.
Yes. But there's things you want to know about them, properties they have, and this and that, right? And it's not necessarily.
Well, do we have entities for them?
No, not that I know of.
Maybe we should, because that way we can have a computable version of the properties. Right, just like we have entities for plane curves and God knows what else. I think it's a good idea to have entities. It's rather easy to do. Whatever you're assembling with the properties, you can make it into an entity store, which means they just directly flow through. That's a simple idea, but what's that?
Someone sneezed.
That was a sneeze. I missed my mute.
No problem.
Well.
I mean, this is the kind of thing I'm talking about. Okay, trapezoid. What's this? Okay, there it is, right? Oops. There's a bug. Somebody please make a note. Wrong capitalization there. Anybody get that?
Yes.
Okay, but this is the type of thing, and that seems useful to me for these types of matrices, right, Roger?
I don't know. I mean,
well, if it's useful to have a handbook, it's useful to have an entity store.
Okay. Yeah, I haven't tried to sort of decompose it like that.
Right, but to me, it will be useful to know what's a type of matrix that is symmetric and has blah, 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 blah.
Right. But kind of what you want to know is that sort of what are the benefits? You know, where do you gain performance?
I understand, but also
to utilize
if you want to do discovery, then
where does it come from?
Yeah, well, fine. That's a different story. But I think that's a fine idea. But I think that, I mean, okay, I'm going to play back to you something you've played to me, Roger.
Okay.
These are special matrices.
Yes, they are.
Where's the general matrix?
The general matrix is a dense general matrix.
Really?
Yes.
There's no general special matrix. Like there's no generator of matrices somehow. I mean, in other words, okay, to put it this way, and this was, you know, a matrix can be thought
actually,
of
now that you say that,
actually,
Devendra, one thing we missed here are these random matrices. Those are usually structured. They're definitely.
Yeah, I think we have a long list of them. The problem is I mean, honestly, it means working with other people's code. I mean, like, so we have that on. I'll make a note again, but we have a long list of things which can be done, so to speak, but we haven't got around to them because, I mean, we also need this layer that we have right now to do all that. So I made a note though.
Okay, good.
Well, you're talking about a random Hilbert matrix or something.
No, random matrix theory, and they don't.
No, I know. Yeah,
but they don't give you kind of a random Hilbert matrix isn't super hard to do because it has such a nice.
No, I know it's a Gaussian orthogonal ensemble and this guy.
Yes, those guys.
Yeah. Right. So now that we have the orthogonal, we can then go on to the next layer, which is to use them in statistics. So we're doing a bit in geometry now, but we have other areas which can now benefit from this structured framework. That's
okay, but I'm going to claim that the general special matrix is function matrix.
Where you get, well, yes, sure. You know, table of each element.
Well, it's array, really. That's really array.
Right. Yeah.
But the point about function matrix would be, if it made any sense, would be that it is an unevaluated, because that's the whole point, that you don't want, it isn't dense, you know, it's not turning it into a dense matrix.
Right. Well, yes. I mean, that's what these structured guys do.
Right. But what operations could you actually do on this?
I don't know. I mean, but you might be able to do like a determinant, and for example, it probes values of f. And once it finds one of them as 0, it's like, oh, I don't need to compute a bunch of others.
Well, we do that.
Yeah, today. I mean, there's one thing that we already are coming across, that some of our linear algebra algorithms already optimized for the kind of thing you're saying. Like they do know about symmetric matrices internally.
Some.
No, I understand it. But what I'm saying is this, okay? I'm saying is this, that let's imagine that's not 6, but it's 1,000,000. Okay?
Yes.
Mm-hmm.
And you start probing this thing, and you find enough zeros that you say, "Up, this determinant is 0."
Right. So, right, we don't. I mean, we usually call them sequences. This is a bivariate sequence, but and at that level we can do things. You know, that's like the discrete calculus story. Yeah. But we haven't done the sort of linear algebra story on that.
I think it'd be worth thinking formula. About. I mean, I'm just playing you back what you played to me.
No, I realize that. I mean, they are using that, Stephen, but they're using sort of known important classes.
I get it. But so my question is, how general can it be? And maybe there's a framework. It's just a suggestion.
Yeah.
What the hell is that little blob there? Bug. It's a floating bug.
Actually, now that you mention it, Stephen,
what blob are you talking about?
The bottom left blob that will disappear if I move my mouse to it.
Oh no! That's the show the.
I know what it is. Show the what?
That's to show the value. If you go over like an actual element, right, it gives you the index.
No, I understand, but why is it there? Why is it there when it's the up arrow thing? Why is there an empty blob looking silly?
Well, maybe that's a bug, but right, it's because the thing appears when you're over the data set.
I know.
I was going to say, Stephen, that there is actually some of these things that we have, like Vandermonde and other things. You can do that on, so formula based, just like what you say with Fs there.
Mm-hmm.
And particularly for like evaluating determinants.
Yep.
So you can have like hypergeometric term structure and things like that you can take advantage of. We haven't added those classes here because they need to sort of come up in applications enough, it feels like.
Yeah. Anyway, I'm suggesting think about maybe irrelevant. Okay, Jeremy, are you ready to show us something?
Yeah, I mailed you something. I have it in Photoshop too.
Okay, hold on.
You saved that notebook with that bug, so I can take a look. Because I don't think it happens with any data set. Thanks.
Okay. I like this.
Yeah.
I like that quite a bit. We need to check what happens when there are more numbers and things. We maybe could darken the 5 there, but I think that's pretty nice. Now, what's this? That was just a sample, right? Because that's nothing to do with that. That isn't.
That was the first thing we talked about, making the F smaller, whether or not the chevron would show up. I just changed
it. At all. It should be. We should go to a thing like this where the F is sitting inside here.
Okay.
I think it should go here, and I think that forget the chevron, and we should tuck we should have an F kind of as an iconic F, and then we should have the 5 to the 2 underneath it. Shaded by the fronds of the F.
Oh, do you want a hover effect or something that knows?
Yeah, hover effect.
Yeah, okay.
Hover effect.
Yep.
Yeah, I think this is nice. Roger, what do you think of this?
Yeah, I think it's a good idea.
Well,
and I like the general theme that they're kind of effectively different types that are kind of very compound inside.
Yeah.
But it's like,
are you?
Yes, well, I'm right. I'm concerned. By having it sort of inside the circle instead of just a normal superscript, I'm worried about the scalability. If there's multiple numbers or if it's just a big number.
We have to worry about how it's actually implemented. Yes, I agree. But I suspect we can do this with. And we need to make sure that magnification works, etc., etc., etc. But at least we've got a target here, which I think looks nice.
Okay.
Okay. Wow. Is there a lot of stuff here, in fact, in this n-line integrate?
It's just exactly the same spec, but the full battery of numerical options to control.
Okay.
Accuracy go, precision go.
All right,
working
fine.
precision.
Does that work? numerical contour integration?
Yes.
And it doesn't give stupid answers for. And what happens if you're on an infinite contour? Does it work? Like I mean, we were going to have named contours like the Bromwich contour and things like this, right?
Devendra.
What's that?
Devendra.
Yes, so you might even have a kind of, like a couple of poles on the x-axis which you want to exclude. We would try to do the, kind of the limiting case numerically, yes. So it tries to imitate all of contour integrate. They'll have the pluses and minuses. But the main point over here is that people are already asking us to tech support for the numerical versions because they don't get it how to use, when to use symbolic, when to use numeric. So to answer your question, yes, we've tried to imitate the entire framework for, and we do it for an inverse Laplace transform, basically.
Yeah.
So, okay, so to be very honest, we might even be using the inverse Laplace transform internally once in a way, just to get to the right answer.
Do we have ND yet after all these years?
No.
ND, N limit, N whatever, all pending.
Yeah.
Just
We don't
we'll
have
probably what we'll probably do is tackle them in a calculus and algebra team instead of the numerics team.
Makes sense to me. Because they need a bunch of pre-processing things, don't they?
Yes.
yes.
And you have to be pretty clever, actually, for that to be.
I'm sure so.
And to be useful, yeah.
Okay. All right. So my question about named contours, could you answer that?
Yes. So we have done that for the 13th release. We have tried to imitate that for the N case. By
how much? What did we have as name? I mean, like the famous contour, the Bromwich contour for inverse Laplace transform.
Well, in that case, you might need to specify because I don't think we had Bromwich as a name, but we had got other things like in the semicircular contour with a couple of arcs sticking out of the x-axis.
Do we have names? Are they string names or what are they?
Yeah, they're string names. Yes,
they're on the ref page if you want to look at them. But
they're
on what?
On the ref page, on
exactly
contour integrate.
Yeah, they have the full battery of names.
It's in the notes with pictures and everything.
Oh, lovely.
Yeah, so we've just imitated the entire. This structure has now been carried over to N contour integrate. And if you have things which are infinitesimal, we try and do something sensible with the numerical methods.
Wait. I mean, the contour that one often uses is this vertical contour,
right? But that's
and then going off to the left, right?
But that's easy to specify, right? Because you can just do from C, if that's what you mean, like from minus infinity to infinity. So like 2 minus.
No. The contour for the inverse Laplace transform. If I'm not mistaking it.
Yeah.
Yes, it's a vertical
So vertical line going from C minus I times infinity to C plus I times infinity.
Right. Then with a left hand.
Yes.
Kind of thing. So why don't we have? I mean, isn't that a very famous contour?
Yeah, but we haven't named it over here. I mean, it's available quite easily. So I think naming it would
why is it available so easily? I don't understand how I make
because you can just say an infinite line.
Yeah, exactly.
How does it close? How does it know to close to the left?
Well, I mean because we have an orientation notion. So I think that's okay. I think we're going up, right? So yeah. And then the question, should we call it Mellin or in Laplace? See, we got these different things in the system which have got very similar kinds of framework. So that's a little harder to.
What? For that contour?
No, I'm just saying that, what do you call it? Is it
called what?
The contour for Bromwich, right? It's also related to the contour for Mellin, inverse Mellin, for example. So we got these different kinds of things in the system which essentially are related. So we didn't give them a special name. That's what I'm saying.
Except that if people are looking for the Bromwich contour, which I think they would do in complex analysis.
Okay.
We should let them find it.
Fine. I think it'd be good to have that condition. Fine. Yes.
Like I'm sure if I do a search for Bromwich, I will completely not find anything, which is wrong.
Yeah.
Yes. Well, it might come up with inverse Laplace transform if it looks at our keywords. Look at that.
Amazing.
But now you're seeing now that there's inverse Laplace and inverse Mel in both. They're kind of very close related. So which one do you?
What? It's still called the Bromwich-Kontoff in both cases, right?
That's fine. Yeah, we'll do that. No problem. We'll have Bromwich.
Yeah.
Agree completely. No problem.
So this is expanding.
That's a good idea.
The input language to take some other things that effectively are differential equations.
Yeah, that's interesting. I've been wondering about that.
Yeah, we've worked with Subha for this, Subha Thomas, and it's quite a bit of effort and thought has gone into it.
Can I ask this question? If I just want the ODE out of the state space model, how do I get that?
There's a property for state space model, I think. If you want to extract the ODE, I can't remember if it's a documented property or.
Well, we need to make sure it is, because I mean, by the time you've got the solution, you better be able to get the ODE as well.
Well, I mean, we use it here, but I can't remember exactly. It's.
No, but what I'm saying is,
can we take that note down and we'll check on it. I'll check it right now, actually.
Now, why didn't that autocomplete? Why is that not auto-completing?
What is not auto-completing?
This property here. It should autocomplete. Why the heck isn't that auto-completing? Somebody forgot to put that into the auto-completion system.
Well, no, because if it's a head,
it knows how to do it. It does it on millions of other heads.
Yes, but that requires support in the C++ in the front end C++ code. That's not something
not for a specific head. They have a way of doing it for generic heads. It should work.
So it's the other way around. It transfer. You can give differential equations and get a state space model, but there is no blessed way to get them out.
So we need that, right? Just like we can get the solution out, we need to be able to get the equation out.
Sure.
I mean, this is lovely. Who needs to feed it to an Arduino when you can just get a formula? That was a specious comment.
Right.
Well, this is very weird. This is very weird. I don't understand this.
I missed your screen.
I'm not understanding this.
I missed your screen a little bit. Okay. Where were you? Which example?
I was over here. I mean, okay. So the problem is, if I say desolve, I can't do that here because this doesn't have variables.
Yes, exactly.
It's a bit of a hackosaurus.
Yes, and we couldn't see so the other point is then if you're going to get all the equations, do everything, then you're kind of handing everything to the user.
No, I know. I'm not suggesting we do that. I think that this is a good way that is really hang around state space model.
Yes.
Right?
Yes.
Now, I don't understand. What's the sign T doing?
Input.
Oh, God.
These things these are not like, they need inputs. That's the whole point of these systems.
This is getting more and more hacky.
Why can't we do this in desolve?
Because desolve will not allow you, you need to specify your variable very explicitly, and you can only solve for the very narrow range of variables which are themselves. Desolve value will allow arbitrary expressions, so you can do it over here. So you don't actually need.
Okay, look. The problem is the state space model is essentially a left-hand side of an ODE. Is that true?
It's the full system.
No,
no. Well, what's this then? This is a driving function.
Yes,
which appears in the ODE.
Yes.
Right. So,
but there's something. There's something that sits in. There might be more than one. First of all, and there's some way that they come in and affect the state, which is that B matrix there, and the D matrix. The B matrix is how it affects the state, and the D matrix is how it affects the output. This is super simple one-by-one system. So it's
look, I really like the idea of sort of connecting these control system type things to our whole symbolic framework like this. I'm not totally convinced this is the right way to do it.
I'm not 100% either, but I wouldn't mind iterating one go with something experimental support.
Well, I know, but we need to cover this another time. We're running out of time here, so I'm just trying to get some scope here.
Then we got Laplace convolve. So that's just the finite convolution from 0 to t instead of negative. So that's the one that interacts well with the Laplace transform. So convolve is on the whole real line, the integration, and interacts with the Fourier transform. So what we're lacking was for a long time was a Laplace convolve, which does kind of causal convolution.
I'm confused.
Well, the output, a convolution is another way to describe what a system does, a filter does. Like that.
Why are there only? I mean, in this case, it's f convolve g with x being the independent variable, right?
Yes, and
y is the new independent variable. It's like a matrix multiply type thing.
Okay, so why does this? So this has 4 arguments as well.
Yeah.
convolve has
The difference is that it doesn't do the full real line. It does the half line. So that means that if
why
you think
doesn't
of
every
this,
orthogonal polynomial get one of these?
say it again.
Why doesn't every orthogonal polynomial get one of these, like a Bessel convolve and a Hankel convolve, and so on? Or am I missing something?
I think it's just that
those are not used.
Exactly.
Who uses those? I mean, who uses those?
It's very hard to compute them. It's very hard to compute them. These
but
are
who
kind
uses them? First of all, I mean, who cares?
Yeah, I'm just asking a question.
This is super used. Okay, so for all things that that have initial value and output, you typically don't want the output to depend on the future. It has to depend on the history only.
There's a one-sided integral as opposed to the convolve, which is from -infinity to infinity.
Right,
exactly.
right.
And why do
users keep asking for it?
Fifth argument that goes 0 to infinity or something? Is that useful or not?
We discussed that it looks like we're changing the kind of what the output means. So it looked like this was required on the continuous side because people would think convolve did what you're saying. It went from 0 to infinity, but it doesn't. So
is Laplace convolve the right name for the one that goes from -0?
Okay, so that's actually there's a question there. If we do this, we have to do Z convolve, like for the discrete convolve.
Exactly.
Another potential naming convention could be
convolve or something.
Causal or unilateral. I think are the two potential.
I mean, then you only need to distinguish between the discrete and the continuous case somehow.
I mean, I'd call it a one-sided convolve, but maybe unilateral. I guess
I guess
it's another way of saying unilateral.
We didn't call the Laplace transform two-sided. We call it bilateral, right?
Yeah, okay.
So
this again is going to need a bit more discussion. I get the point, but I mean, I don't understand why there isn't a fifth argument to convolve anyway that just gives, or you say it's only computable for the 0 infinity and -infinity infinity.
No, it's not. But I think that this is like one of these common utilities. It should be simple.
Yeah. All right, okay, fine.
Yeah, and we're writing a book which uses all the time, so I think it'd be good to have it built in and consistent with the rest of the.
Okay, but is Laplace convolve the right thing, Monsieur Pierre Simon, whatever Pierre? What was his name?
Well, it's not a bad name.
Yeah.
Okay. As opposed to causal, I mean, we're going to have a bunch of other functions. All this multi-computation stuff that I've been working on is going to have a whole bunch of causal, this, that, and the other functions.
Yeah.
But you know that whole system modeler is acausal.
Yes, I know.
Okay.
So, like Roger said, we'll have Laplace for the continuous case and Z for the discrete case. Then we have clear-cut names which suggest what convolution they're good for. I mean, like in this case, Laplace, in the other case, Z. So in retrospect, maybe the first one should have been called Fourier convolve.
Well, I don't know.
Yeah, I don't think
convolve
so.
is the right
I
thing.
mean, I'm just, we normally
No,
don't do that.
people usually define the convolution and they call it convolve, but they define it secretly somewhere. So if you read a signal processing book, it's actually this Fourier convolve, because they use bilateral Laplace transform and Fourier transforms in control and
I need to go
things
to something else. We need another episode of this.
Okay.
All right.
All right.
See you guys soon. Thanks.
See you. Bye.
Okay. Bye.
Devendra and Adam, are we still having our meeting?